Let me record this class. Class is being recorded now.
Can you see my screen?
Yes.
Here's question 12. Oh, a bus travels between the two cities, A and B, which are 100 miles apart. If the bus has a breakdown, the distance from the breakdown to city A has a uniform distribution over parentheses 0, 100. There's a bus service station in the city A in B, and in the center of the loop between A and B. It is suggested that it would be more efficient to have the three stations located in 25, 50, and 75 miles respectively from A. Do you agree? And why? So first of all, we know the distance between A and B is 100, so we just draw it out and from 0 to 100. And then the bus has a breakdown, so whenever the breakdown happens, people from the bus need to get off the bus and then go to the nearest bus station. Since the difference between the difference of speed between a human and the bus are very huge, we only consider the time spent on people.
Sorry, hold on, Jie, hold on. I think I did something wrong. I removed how. So I meant to make him a presenter. Somehow I think I did the wrong button. How do I recover that?
I don't know.
Let me see. Hold on 1 second. Let me try this. How did I remove him? Oh, remove from session. Oh my goodness, what did I do? Let me see. How do I? This is awkward. Maybe my finger just sliced on. Okay, so how do I get him back? It shows removed, which means I probably pressed the wrong button or somehow. This is awkward. I remember I did another time with another class. I can only hide. Let me see if what if I do this? Setting one issue. No good. Okay, just hold on 1 second. Let me send him an email. I think I did something horrible. Okay, let's see what's happened. Sorry. Okay, Jack, keep going.
Okay. Since the difference of speed between human and bus are very huge, in this case we consider the expect mile people walk to the bus station when breakdown happen. when the next when the expected value is less to be efficient. Okay, and then for here we have the distance from breakdown to CDA has a uniform distribution over 0, 100. So the g of x be the uniformly distributive probability density function. That'll be 1 over 100. And that also tells us is from B to A. And for the first case would be current plane. And we gonna calculate the expected mile and then compare the current plane and the suggested plane. For the current plane, we have a bus station in A, so station 3 here, and station 2 in the middle. That would be the center of the loop between A and B, and in B. So there are 3 stations. Okay, and then we let fx be the distance to the nearest bus station. So, and then we give 2 midpoint between each of 2 stations. So the midpoint here is 25. So whenever the x happened in the left of 25, that means the nearest station is station 1. When it happens on the right of this 25, that means the nearest station is station 2. And similarly for this one. And then we have a distance and then we have the f of x is the distance to the nearest bus station. And originally, we regard the destination as the bus station, and the location is miles when the breakdown happens. So that the distance will be the destination minus the location. And then since the distance is sent like a location, the distance from destination to the location is sent like the distance from location to the destination. So we can swap the property. So we have the destination be the x and the location be the station. And wherever the x happens between 0 and 25 miles, we have destination minus the location will be x minus 0, because the location is in station 1, that would be 0. And similarly, when the breakdown happens between 25 and 75, we have x minus 50. And when it happens between 75 and 100, it would be x minus 100. And then we got to convert we got to get rid of the absolute value. So regard the S1 as the origin. So 25 would be 25, 0. And it's positive, so we just leave it as x. But in the second case, we have if we regard the S2 be the origin, we have the first part would be negative 25, 0 to the 0. That would be the negative. So we have to add a negative sign to the absolute value and get rid of the absolute value. We got the 50 minus x. So that would be the second line. And when it's positive, and when 50 to 75, that would be positive. So that would just be x minus 50. And for the 75 to 100, we consider 75 as the origin. So that would be 0 to 25. That's also positive. So that would just be, we consider S3 here. We consider here as the origin. So that would be negative 25 to 0. That's negative. And then we just add the negative sign and we get rid of the absolute value sign. We got 100 minus x. And that represents the distance to the nearest station.
Okay.
And then we gotta calculate the expected value of it and of the distance to the nearest bus station. Since we have the density function and we have the real value function, and we want to find the expected value of the real function, real value function. That will be equal to the density function times the real value function, and this represents the density function, that's g of x, and this will be the fx as the real value function. And we calculate it, we integrate it, we got the expected value will be 12.5. That's the current plan. And similarly for the suggested plan, we have 25, 50, and 75 miles from A. So 75 miles from A would be this one, and 50, 25. And similarly, we find the midpoint of those two, and then we find the distance from here to here, that is go to station 1, and from here to here to here, we go to station 2, and from here to here, we go to station 3. And similarly, we want to get rid of the absolute value sign, and we got those 6 lines, and then we integrate it. And we got the expected value would be 9.375. And that implies for the suggested plan, the expected amount of people walk to the bus station is less than the original plan. So I would say agree.
Yeah, so okay, so the suggestion works. I see.
Yeah.
Wow. Okay, a lot of work. All right, thank you. Great.
Thank you.
Thank you. Okay, next one. Catherine, how logged back in? How, what happened to you? Did I remove you? Anyway,
Yeah,
okay.
it's on the blackboard.
Hi, Professor.
Oh, okay. Maybe my fingers just, you know, slip on the option of remove. Okay, Catherine, go ahead.
Hi, Professor. Okay.
Hello.
I'm presenting question 19. So, let x be an exponentially distributed random variable with the mean 1/2. The final value of c for which probability that x is greater than c is equal to 0.25. So, since we know the mean is 1/2, lambda is equals to 2 because the mean of the exponential is the reciprocal of its parameter lambda. And for this question, we use the CDF, the cumulative distributive function, that is a probability that x is less than or equal to a equals to 1 minus e to the exponent of negative lambda times a. For this one, since we know lambda is 2, and for this one, we have to figure out the probability that x is less than or equal to c. So we know is equal to 1 minus probability that x greater than c is 0.75. So we now know that it's 0.75. Using CDF is 1 minus e to the power of negative lambda c equals 0.75. And then we plug in the lambda equals to 2. That gives us 1 minus e to the power negative 2c equals to 0.75. And the result would be like, to get a c equals to ln2 is 0.6931.
Nice. Nice. Okay, so you are ahead of us. You are using exponential distribution already. And great. Great. Thank you.
Hi, Professor. Good evening.
Hello, Itera. Go ahead.
Okay, Professor, I'm going to share my screen. So can you see
Yes.
my screen?
Yeah.
I'm going to present question number 17 of chapter 5. The question is, the salaries of physicians in a certain specialty are approximately normally distributed. If 25% of these physicians earn less than $180,000 and 25% earn more than $320,000, approximately, what fraction earn A part is less than $200,000 and B part is between $280,000 and $320,000. So, from the information, we observe that the salaries of physicians in a certain specialty are approximately normally distributed. If 25% of these physicians earn less than $180,000 and 25 earn more than $320,000, consider X is the random variable that represents the salary in thousands of dollars. So from the question, we have that probability into X less than 180 is equal to 0.25. For the normal distribution, we have probability into X minus mu over sigma less than 180 minus mu over um, uh, sigma, which is equal to 0.25, which is given in the question. So for that, from the standard normal table values, observe that the critical value of Z for the one tail test and the corresponding cumulative area of 0.25 is minus 0.675. So it will be 180 minus mu over sigma is equal to minus 0.675. So after calculation, we will get the equation 180 is equal to mu minus 0.675 sigma. So for the second part, like that probability X greater than 320, it will also equal to 0.25. It is given in the question. So then we have standard deviation formula probability into X minus mu over sigma. And when we put the value of X there, we will get 320 minus mu over sigma, which is also equal to 0.25. So we have 1 minus probability into Z less than equal to small z is equal to 0.25. Also we have 0.75 for part 1 and 2. We get that 0.75. From the standard normal table, we get the value of Z, which is equal to 0.675. We get these value of Z in the from the table of Z. So after that, 320 minus mu over sigma is equal to 0.675, and we will make, when we will make the equation, then we will get 320 is equal to mu plus 0.675 mu. And after solving both equation, we will get the value of mu, which is equal to 250, which is mean, basically. Substitute mu in the equation, then we will get the standard deviation, which will be equal to 103 minus 103.704. Therefore, I told you that mu is equal to mean and sigma is equal to standard deviation. So for the A part, which is in the question, we tell that you have to find the normal distribution less than $200,000. So for this part, we have probability X less than $200,000, and we will put this in the formula of normal distribution. So then from this thing, after calculation, we will get 0.3149. And similarly, for the B part, which is given in the question, that between $280,000 and $320,000. So for this thing, we have normal distribution formula like this. And then after putting the value, we will get that 0.1348.
Great. I like this. Yeah, this is a very good question. Very good question and very well presented for normal distribution. Very good, very nice. You form the system of two equations with two variables to solve the variance and the sigma, mu and sigma.
Yes, Professor.
Great. Yeah.
Thank you. Thank you so much.
Oh, you're welcome. Thank you. Yes, you care. So who's next? So I have a Hall, Tom. Right. We're only left with you two. Anyone else like to present as well? Yet, okay. Yeah. Anyone else, especially for those ones you haven't been presenting for a while? 20% of your grades will come, at least 20% grades will come from your presentation. And also, you know, your extra credits will come from your presentation as well.
My question is 5.13. A shuttle bus completes the journey from an airport to a nearby city and back every 15 minutes. A, if the waiting time has a uniform distribution, what is the probability that a passenger has to wait more than 6 minutes for a shuttle train? B, given that a passenger has already waited for 8 minutes, what is the probability that he or she has to wait an additional 2 minutes or more for a shuttle train? Since it goes back at 15 minutes, I found out that the probability density function of x is 1/15. Then going to A, it says that more than 6 minutes, it will be probability of x greater than or equal to 6. Then taking the integrals from 6 to 15 of 1/15 dx, you integrate it to get 1/15x. Then you plug in to get 0.6. And for B, says that it's from probability of x greater than 10 given by x equal to the time is you already waited for 8 minutes. So it's the x greater than 10 over x equal to 8. You get you plug in a number 15 minus 10 and 15 minus 8 to get 5/7.
I see. Okay, nice. I want to ask you, so you are being removed because I hit the remove button, I guess, right?
Yeah.
I just want to make sure.
Because
So when I do that,
I just see that I have been removed it.
So what happened? When I remove,
I don't know. Just like I try to join, it shows a mentor remove you.
I remember long ago when the COVID first hit, you know, I did this same thing with my another class. But so if I click on this, right, it's the option of the last option, remove from session. I'm so sorry, because I saw you.
Yeah.
It showed say you are being removed. I was like, what? I did this again. Sorry.
That's
All right.
I'm still in the class right now.
Yeah, I was worried that you are not being. I sent you an email. I was worried you're not being able to come back. Okay, great. All right, I think Tom, Tom and Ayat. So two of you. All right, I guess that's Tom's, right? Or that's 522. Who's this? Tom.
Okay. Okay, the question is, currently I'm throwing darts at a dashboard, or dartboard repeatedly. Each of his throws are independent with success rate P equals 0.5. hitting bullseye, what is the approximate probability that Tom takes more than 50 throws to hit the bullseye? So that's equivalent to up to 50 failures, then success. So start off, question is asking approximate probability. So we have a comparison between the actual value, which is a discrete random variable, x, which is the number of throws until it hits the bullseye. So from chapter 4, this is a discrete geometric random variable with probability of success 0.05. Q is 1 minus 0.5, which is 0.95. So probability x is greater than 50. It's going to be equal to 1 minus probability x less than equal to 50. And so to get less than equal to 50, we're going to have a summation from trials from 1 to 50, which is up to 49 failures, and then a success. So that's why the values is from 1 to 49, or 0 to 49. Because if you have 0 failures and then 1 success, we also want to subtract that. So then for the discrete scenario, we get 7.6%. And then, well, we're supposed to get the approximate probability. So we're going to compare that to the continuous probability density function. So we have going to be integrating this function from 0. Well, the exponent is x minus 1 because we always have one less. We always have a failure that's one less than the total trials. Like if we have 50 trials, we have 49 failures. So that's why the exponent is x minus 1. And the probability density function is 0.05 times the integral 50 to 0 of 0.95 to the x minus 1 power. And so we integrate that, and then we get 10.41%. So when we use the continuous, the PDF, we're going to get a slightly off answer because it's a discrete random variable.
So why
yeah, we're basically taking like values that are not really in the in what we're looking for. Like we're not looking for 0.5, for example, or 1.5 or 2.5. But the PDF is taking all the area under that curve. And, yeah. So that's why it's approximate probability.
I see. So one is 7.6%, one is 10.41%. So what conclusion you can draw from this?
So you wouldn't want to use a PDF for a discrete variable because your integration is taking in inputs that are not part of what you're looking for, because the inputs should be countable numbers from 0 to like 50 trials, but we're taking in trials that are like the decimal values, like 0.1.
That's right.
So on.
Right. Good. Good. It's all about the conclusion. All right. Thank you, Tom. You always pick interesting questions. Great. Right, Catherine saying you picked up the question with your own name. That's great. All right. I think Aya, you're the last one.
Yeah, I'm here. Okay. So that's a pretty simple question, which the height x in centimeters of adult woman is normally distributed with a mean 165 centimeters, 165, and standard deviation 6.5 centimeters. So we have to compute probability of X more than 160 in A. So what is given is mean, mu, which is equal to 165, and standard deviation sigma equals to 6.5. Okay, so probability of X more than 160. Here I use the Z, which is equal to X minus mean over standard deviation. So probability of X more than 160 is the same as probability of Z more than 160 minus 165 over 6.5. It's probability of Z more than minus 0.77. The table in textbook doesn't have negative numbers for Z, so I used a positive number, Z equal to less than 0.77. So I depict the graph of bell shape distribution, normal distribution. The probability of Z more than minus 0.77 is the same as probability of Z less than 0.77. So, and it equals to 77.9%. Okay, next question is X more than 163 and less than 167. So it equals to difference between probability of X less than 167 and probability of X less than 163. Okay, so it's the same as the probability Z of Z less than 0.331 and minus probability of Z less than minus 0.31. And it equals to 24%. Okay, next one is probability of X less than 164 is equals to probability of Z less than minus 0.15. Is equal to 1 minus probability of Z less than 0.15. It equals to 44%. Okay, for D, probability of X more than 171 is equals to probability of Z more than 0.92, and it equals to 1 minus probability of Z less than 0.92. So it's 17.9%. And the last one is short. It's probability of X less than 168 is equal to probability of Z less than 0.46, which is 67.7%.
Nice, very interesting.
Yeah, we use I use the table, not calculator, table for Z, and it has only positive numbers. That's why I had to play with this table.
Yeah, that's nice. Yeah, because because the symmetry of the bell shape, right? We can always do that. Yeah, yeah. Thank you. All right. Anyone else like to present today? Okay, for chapter 5, where we talk about the uniform, we talk about a normal. We're not going to do the normal approximation to the binomial distribution. Exponential. I think exponential is on the syllabus. Let me just double check syllabus. Let me actually show you as well. See what's left. Uniform random, normal random, exponential, gamma, beta, Cauchy. Then we go to the next chapter. All right. Okay, so today we're going to talk about exponential. The next class, we're going to talk about gamma, Cauchy, and beta. Then we're going to skip 5.7, go to chapter 6. So when we come back from spring break, yeah, we should hit for chapter 6. So exponential, Catherine already showed us about exponential distribution. Okay. Exponential random variable, a continuous random variable whose probability density function is given as so: lambda e to the negative lambda x for x non-negative. If it's zero, if it's negative, it's zero otherwise. So this is called exponential random variable with parameter lambda. The cumulative distribution function, capital letter F of A, is defined the same way, just with a different density function. Right? So it's also the probability of x less than or equal to a certain number. It's the integration from 0 up to this number, and the density function, integrated density function. And you can prove that this equals 1, so it can be a probability distribution. So the parameter lambda will now to be shown to equal the reciprocal of the expected value. So the multiplicative inverse of, so basically it's 1 over e of x. So let's see this proof. X is exponential random variable with a parameter lambda. We want to calculate expected value and its variance. So the density function is defined so, and we calculate the expected value, integration from 0 up to infinity, and x raised by n. Okay, I wonder why x raised by n is not x squared. So integration by parts. We have this, we have this. Yeah. Okay, I'm trying to figure out why this is a 0. And I guess this process has to be repeated. So in the end, oh, okay. So you see this. This is the expectation of x raised by n. And with this relation is n over lambda, expected value to the x raised by n minus 1. So now letting n equals 1 and n equals 2. So that gives expected value of x equals 1 over lambda. And the 2, we get 2 over lambda square, right? Because 2 is 2 over lambda times expected value. So that's 1 over lambda. That's why this is 2 over lambda square. So the variance is 2 over lambda square minus this, so which is 1 over lambda square. Very interesting, huh? So this is for exponential random variable. The expected value is 1 over lambda. The variance is 1 over lambda squared. Okay, let's see. In practice, the exponential distribution often arises as the distribution of the amount of time until some specific event occurs. For instance, the amount of time starting from now until an earthquake occurs, or until a new war breaks out, or until a telephone call you receive turns out to be a wrong number, are all random variables that tend in practice to have exponential distributions. Let's see an example. Suppose that the length of a phone call in minutes is an exponential random variable with parameter lambda equals 1/10. If someone arrives immediately ahead of at a public telephone booth, find the probability that you will have to wait more than 10 minutes, between 10 and 20 minutes. Okay, so let X denote the length of call made by the person in the booth. Then the desired probability is more than 10 minutes is 1 minus X less than or equal to 10 minutes. If we do the calculation, that would be 1 over E. In between 10 and 20 minutes, that's this X less than or 20 minutes. That's F of 20 minus F of 10. Right, because this is X greater than 10. So if we do the calculation, is 1 over E minus 1 over E squared. We see that a non-negative random variable X is memoryless if X is greater than X plus T, given X is greater than T, equals to probability of X greater than S. Memoryless, so T doesn't do anything much. If we think of X as being the lifetime of some instrument, the above memoryless equation states that the probability that the instrument survives for at least X plus T hours, given that it has survived T hours, is the same as the initial probability that it survives for at least S hours. In other words, if the instrument is alive at HT, the distribution of the remaining amount of time that it survives is the same as the original lifetime distribution. How nice if this is true for human life. Okay, anyway. Okay, let's see example 5C. Consider a post office that's staffed by 2 clerks. Suppose that when Mr. Smith enters the system, he discovers that Miss Jones is being served by one of the clerks and Mr. Brown by the other. Suppose also that Miss Smith is told that his service will begin as soon as either Miss Jones or Mr. Brown leaves. If the amount of time that a clerk spends with a customer is exponentially distributed with parameter lambda, what is the probability that of the 3 customers, Mr. Smith is the last to leave the post office? So the reasoning is this. Consider the time at which Mr. Smith first finds a free clerk. At this point, either Miss Jones or Mr. Brown would have just left, and the other one would still be in service. What if both of them leave the same time? However, because the exponential is memoryless, it follows that the additional amount of time that this other person would still have to spend in the post office is exponentially distributed with parameter number. That is, it's the same as if service for the person were just starting at this point. Okay. Hence, by symmetry, the probability that the remaining person finishes before Smith leaves must equals the half. All right. Does this make sense to you guys? Well, anyone has any questions? Okay, anyway, this is not important. It's just for fun. It's not important for us. What's important for us is just to, it's very simple. What's important for us is just these three things. The distribution density function, you know, for whatever model we talk about here, Poisson, uniform, normal distribution is quite difficult to remember, but if needed, it will be provided. And the exponential, and also their variance, the formula for their variance and expected value. That's what's important. And of course, know how to apply in life, right? Okay. Let's see some real examples. Let's see, these should be real examples. Suppose the number of miles that a car can run before its battery wears out is exponentially distributed with an average value of 10,000 miles. If a person desires to take a 5,000-mile trip, what is the probability that he or she will be able to complete the trip without having to replace the car battery? What can be said when the distribution is not exponential? Okay, let's see this. It follows by the memoryless property of the exponential distribution that the remaining lifetime in thousands of miles of the battery is exponential with parameter number equals to 1/10. Hence, the desired probability is remaining lifetime greater than 5 because it's in 1,000 miles. Right? Because it's in 1,000 miles, that's why this is 1/10. This is only 5. So there's 1 minus f of less than or equal to 5. The plug into the distribution density function, that's e to the negative 5 times 1/10, which is e to the negative half, or 1 over square root of e. That's about this much, or 61%. However, if the lifetime distribution f is not exponential, then the relevant probability is lifetime greater than t plus 5, given the lifetime is greater than t, is 1 minus f of x less than or equal to t plus 5 divided by 1 minus f of t, right? Because the numerator is f x greater than t plus 5. The denominator is x greater than t. So where t is the number of miles that the battery had been in use prior to the start of the trip. Therefore, if the distribution is not exponential, additional information is needed. Right. Let's see this. A distribution of exponential distribution is a distribution of a random variable that's equally likely to be either positive or negative, and whose absolute value is exponentially distributed with the parameter number. Such a random variable, look at this, lambda can be 0. Such a random variable is said to have a Laplace distribution. Okay, Laplace is a famous mathematician, and its density is given this. It's okay, you know, we're not, for our class, we don't care about Laplace. For E. This question happened in 4E. Let's see if we can recall that. Suppose that a binary message is to be transmitted from A to B, with the value 2 being sent when the message is 1, and negative 2 when it's 0. Yes, I remember this. However, suppose now that rather than being a standard and normal random variable, the channel noise n is a Laplace random variable with parameter lambda equals to 1. You know, again, let's not care about Laplace. Let's see this one. One often hears that the death rate of a person who smokes is at each age twice that of a non-smoker. What does this mean? Does it mean that a non-smoker has twice the probability of surviving a given number of years as does a smoker of the same age? Very interesting. If you are interested, you can read this yourself. Okay. Let me see how long is the gamma. Gamma distribution. Beta distribution is all about the formula, beta distribution. And one more is Cauchy distribution. So Cauchy distribution. Oh, I guess I missed. Beta. Oh, Cauchy distribution. Okay, we'll talk about this next class. We're just going to, to know those distributions. All right, Cauchy, beta. There's 3 different kinds of very fancy distributions with density functions. You know, I don't remember them. I never remember them. Gamma distribution, right? Just to have an idea when to apply them, you know, in what kind of situations to apply them, and the formulas we can always look for it. I guess that's it for today. And yeah, we're not going to talk about hazard rate. Again, for exponential distribution, just remember 3 things. The density function, lambda times e to the negative lambda x, then the expected value, 1 over variance, 1 over lambda square. Catherine, next week 5.6. Yeah, next week we'll finish. Not next week. Yes, next week, next Tuesday. After next Tuesday is our spring break. So when we come back, so next week we'll finish chapter 5. So when we come back from spring break, we're going to talk about chapter 6, because we'll have 6, 7, 8 left. And I don't think we're going to details for 6, 7, 8, but to know the important theorems and stuff. All right, guys, have a good night. If you have questions, I'm here. If you don't have questions, go ahead to do your homework. And I haven't finished grading yet. I need to finish grading during the spring break. Okay, bye. Have a good night, Catherine.